As an introduction to this lecture, I want to ask you, do you know why we don't use metal plates for our clothes? Of course, because they have not pores. Because they are too hard and they have not pores, isn't it? Pores are very specific, or the gaps among fibers are very specific behavior of fibrous assembly, which we used very intensively in our clothes. Nevertheless, also for a lot of technical applications, for example, by filtration and so on. Today's lecture will be oriented to the possibility how to model the pores, the gaps among fibers. Let's start with small repetition of our earlier relations, which we derived in lecture 1 about the terms, definitions, relations, and so on. We use symbols T for fiber fineness, S fiber cross-sectional area, ρ material fiber density, D is equivalent fiber diameter, P is fiber circumference, Q fiber shape factor, A is specific fiber surface area, capital L will be total length of fibers in our fiber assembly, A is total surface area of fibers, V is total volume of fibers, VC total volume of fiber assembly, and mu is packing density. We derived for fibers that fiber fineness T is cross-section S times ρ, so that all these relations are valid. Q, fiber shape factor, is defined as a perimeter of fiber cross-section by pi d, the shortest perimeter which is possible for the same area, minus 1, so that fiber perimeter is given by this expression. A, total surface of fibers, it's perimeter of fiber cross-section times total length of fibers. Using equations derived earlier, we obtained these equations, and packing density was defined, then ratio of fiber volume by total volume, where fiber volume is fiber cross-section, or pi d squared by 4 all S times, of course, total length. Let's introduce one new quantity, surface area per unit volume. Surface area of fibers in our fibrous assembly, we said it's this pi d times 1 plus q times L, and the volume of fibers is pi d squared by 4 cross-section times L. From this, gamma, which is A by V, is given by such expression, and in comparison to A, what was A? A, specific fiber surface area, which is here. You can see that the surface per unit volume is specific area, specific fiber surface area, times ρ. Pores. Relatively easy is to obtain a quantity which we call porosity. What is porosity? Among the fibers are some gaps, some space of air. Volume of this space is Vp. Is it P? Yes, Vp, which is total volume minus volume of fibers. Because what is not the fiber volume is the volume of air. I think air who is giving insight, for example, whiskey, isn't it? Usually beside fibers is free air. Well, so that porosity is the ratio volume of pore of air among fibers times total volume. This one, then this one, because it's packing density. Porosity is 1 minus mu. When the packing density is 40%, then porosity is 60%. Better, more precisely, if porosity is 0.6, then packing density is 0.4, and so on. It is easy to obtain. Nevertheless, let's imagine two situations. One box, big box, from compact polyester, and on the center is one big hole. Can you imagine such box? Packing density inside of this box can be, I don't know, maybe 0.5. Let's imagine second box, full of compressed polyester fibers. Packing density is also 0.5. Nevertheless, between these two boxes, high difference with behavior. The behavior of these two boxes are quite other. Why? Because in the first case, the air is in one big hole. In the second case, the air is in a very long path of very small tubes beside by fibers. Therefore, we need also to calculate some dimension of this air of such air space. It is big or very thin. So that we must create something which we will call pores. Starting idea is following. Let's imagine that you have some red pencil. Can you imagine it? That you have some red pencil? Yes, you can. Make between fibers some red lines, as is shown here, and the schematically a scheme of some section of fibrous assembly. Make with your red pen such lines how you want, very subjectively, how you want. This imagination is for this moment. Later, I take you your red pencil back. You will then say it. But now in the moment, because I understand it, please imagine it so. Using your red pencil, you divide the region of air to some tubes having very different shape. Such tubes, now so created, we can call pores. Yeah? The your red lines we will call as a fictive or imaginary borders, because they are not in reality. It's only your fiction. It is only used through your pencil. Well, so each created pore is in contact with fibers, black borders, real borders, and also with other pores in our scheme, using your red pencil. There are fictive borders, yeah? And this tube, this air tube so created, looks like an air fiber. Yeah? Therefore, practically all equations which we derived for fiber are valid also for our air fiber, air tube. These equations which are valid for air tubes, the quantities related to our air tube will have subscript P, like Pore, because this air fiber, this air tube, we call Pore. For example, here is one pore. Black is real borders, red is fictive borders. Area, cross-sectional area of this pore is SP, which is pi dp squared by 4, where dp is this here. dp is equivalent pore diameter. You know this equation from fibers. It was equivalent fiber diameter. Now it is equivalent pore diameter. Well, one difference between our air fibers and real fibers exists in the term of perimeter of pore. In opposite to fibers, the perimeter of pore, to the perimeter of pore, we calculate the real borders only. So that the length of perimeter of pore, our air fiber, is this length, this black length plus this black length plus this black length. But no these red parts. Yeah? Therefore the perimeter length of the perimeter length in pore is shorter than the perimeter from how this term defined in traditional geometry, because the red parts are not our lengths related to perimeter, because it don't exist. It's only your subjective red pencil. Yes, therefore the length of perimeter can be higher but also smaller than the pi d square by 4, dp square by 4. In fiber it is not possible, isn't it? We discussed it. Yeah. All other equations are valid. QP for shape factor, same equation as for fibers, only subscript P. Nevertheless, QP, shape factor of pore, needn't be higher than 0, can be also smaller than 0, because perimeter is without red fictive borders, and it must be higher, equal -1. Well, volume, total pore volume is SP times LP, so that is here, where LP is total length of pores. Sum of all paths through which you can go when you will be so smaller than microbe. Well, total pore surface area, notice perimeter times length, the total pore surface area. Surface area per unit volume of pore, this gamma P, is AP by VP, and using equations derived on the place of AP and the place of VP, which is here in red to shown, after rearranging we obtain gamma P in such form. This part we can jump, you can read it when you want, but it is not too necessary, so that we jump in. The same, this formulation of conventional pore. I will define conventional pore more easier for you. So, we derived equations which are valid for pores, for our air fibers, we can say, air tubes. These equations give together different quantities, different quantities SP, dP, Vp, Ap, Qp, gamma p, which are valid for pores. Nevertheless, we usually we don't know these characteristics. We know the characteristic of fibers. We know fiber diameter because we know fiber fineness. We know fiber surface and so on and so on. How is the relation between pores and fibers? Can we, to obtain something, can we say something about the pores when we know enough quantities related to fibers? How it is? Let's imagine that you are a very small microbe and you are walking inside of our fiber structure through the pore tubes. Because don't go down to your face, your hand will be on the walls around. What is it? What are the walls around you? It is a surface of fibers, isn't it? But this is also surface of pores. So that we can say that the surface of fibers is same than the surface of pores. This idea is not fully clear. Why? Let's imagine the situation which is in our picture. By contact of two fibers, some contact area with red, which is here, related to fiber surface. But it is not, this contact area is not surface, pore surface. It is not part of pore surface, isn't it? So that the pore surface is a little smaller than the surface of fibers. Yeah? But if these contact places are not too large, are limited to point, no too compressed fibrous material and so on, we can say that our starting idea can be as an assumption used. So we will use that surface of fibers, total surface of fibers, is equal to total surface of pores. AP is equal A. Then gamma P was AP by Vp. Because AP is equal A, we can write this black here. We can multiply and divide by blue. It's blue, yeah, it's blue. Blue V. And by green VC, so that we obtain this expression. But this is gamma, this is mu, this is 1 by psi, so 1 by 1 minus mu, so that we can write that gamma P is gamma times mu by 1 minus mu, and gamma P also is, when we use on the place of gamma this expression, although derived earlier, gamma P is this expression. Well, further, using on the gamma P earlier derived equation for gamma 2, we obtain this equation. Here is 4, here is 4, it's going out. And after rearranging, we obtain such expression for dP equivalent pore diameter. It's nice. Q is a as a shape factor of fibers. Mu, it is a packing density. How is the density of fibers in our structure? D is fiber, equivalent fiber diameter. Only one quantity on the right hand side bring us difficulties. QP. What is it QP? QP is a shape factor of pore. But shape factor of pore related to two influences. The first is, how is the structure of our fibrous assembly? If another fibrous assembly, evidently another shape. Second, how was your subjective idea to create fictive borders with your red pen? Because these two influences, we don't know how is the value QP. We don't know the value QP. In this moment is an idea how to very roughly say something to the dimension of these gap-Simmons fibers, independently to them that we don't know the quantity QP. And the people say, well, let's use some convention. Let's say that QP is equal to 0 point. We know that it is not, maybe. But because we don't know what is it, let's use for a rough evaluation, let's use convention only, that QP is equal to 0. If QP is equal to 0, I obtain this equation, isn't it? And it gives me no problem such diameter to calculate. Such diameter I call as a conventional pore diameter. Yeah? Conventional pore diameter you can calculate without knowledge of your, in the moment I say knowledge of your structure of your material, of your fibrous assembly, and you needn't have the knowledge about your earlier work with red pen. Yeah? It's a conventional pore. How is the total length of pores? Area of pores, AP, surface area of pores, we assumed that it is equal to surface area of fibers, A, and for A we know such equation. And because AP was pi times dP times this one, so we can use it. On the place of dP, we use this here. And after rearranging, we obtain LP, total length of pores, as 1 plus Q by 1 plus Q square by 1 plus QP square times mu by 1 minus mu times L. L is total fiber length, possible to calculate it. It's from knowledge of our fibrous material. Packing density, Q, but QP also. Here. Same problem. And same idea, when I know nothing, then I will use some convention. Do you know the term convention? Yeah? Only convention that QP is equal to 0. Then I obtain for total pore length such equation, because this is 1, QP equal 0. This is the total length of conventional pores in our fibrous material. So we define, based on convention, the quantities related to the conventional pore. Every time we are able to calculate conventional properties of conventional pore. The second question is if in our this or that textile structure it corresponds good or bad to real dimension or length of pores. We will see it. Because to illustrate the conventional, in this moment I don't know QP, so that but I can say something about the conventional pores. How is the conventional equivalent diameter of conventional pore? The diameter of conventional pore is shown here based on our earlier equation, this equation, by red curves. So this is a packing density for 0 to 1 on the ordinate quantities of functions used here. Q equals 0, what it means? Cylindrical shape of a fiber cross-section, or fiber, cylindrical fibers. Then the curve is now a dp, then dp star by d, by fiber diameter. This ratio, conventional pore diameter by fiber diameter. This ratio is possible to show here. The function, the course of this function is following. It is with higher is packing density, so smaller is diameter of conventional diameter of pore. And theoretically, if packing density is 1, then the volume of air is 0. In each pore must be volume of pores 0, so the diameter of pore is equal 0. It's well. When we use another type of fiber shape with different values of Q, here are shown 3, 0, 0.25 and 0.5, shape factor of fiber cross-section, then the curves are a little harder, but not too much. So is the relation of conventional pore diameter in relation to packing density. How is with total lengths? Here are the ratio total length of conventional pores by total length of fibers, L, the green curves. By Q equals 0, the curve is increasing. What it means? When we compress our structure, then the symbolically, intuitively say, big hole is derived through fibers which are going inside to the set of small parts between fibers, among fibers. Yeah? So that the length is increasing. The length is really increasing. Higher is a packing density, so higher is increasing function. Yes, by the way, also it is gamma p, which is the dotted black curve, identical with green curve by Q equals 0. You can see it too. So it is the tendency with a conventional pore. We want to be a little more precise, and therefore we will use now another ideas than the easiest idea related to conventional pore, that QP is equal 0. The version 1, the variant 1, based on the assumption pore shape factor QP is independent of the packing density mu. It means when I pressure a material, the dimensions of pores, the pores will be smaller and smaller, but the shape, the character of shape, stay the same. It's some border idea. Okay. How it will be if this is valid? Then QP is permanently same value. 1 plus QP is also for each packing density same value, so that I can call 1 plus QP equal K. Yeah? QP generally can be function of packing density. Now, based on my assumption, I say it is constant, so that 1 plus QP is constant too. So equivalent pore diameter using our starting equation is now this here, and total length of pores, because 1 plus QP is K, is this here. You can say that conventional pore is a special case of this variant 1 when the K is equal 1. Yeah? Well, this is version 1. Let's study another prior assumption. Is here somebody who is smoked? Sometimes. Somebody sometimes. Maybe. Nevertheless, you all know what is it, the filter in cigarettes. In the filter of cigarettes, we can imagine that the air is going beside the fibers and therefore the effect of filtration. This filter we can compress more or less. Nevertheless, the total length of pores, the pores will be bigger or thinner. Nevertheless, the total length of pores maybe is same. Then, from this is going out the second idea, prior idea. Let's imagine that total length of pores is independent of packing density. Total length. No shape of pore, the total length of pores. So, we derived earlier such general equation. We said the problem is our QP. Yeah? Now we must say this equation, this LP is constant. This is the same equation. After rearranging, we can this equation rearrange to this formula. Yeah? It's only rearranging, same equation. Now, length of fibers is constant. Q, fiber shape factor is constant. QP now, QP is not here. LP is total length of pores. Based on our assumption, it is constant. The square root is constant. So that 1 plus QP is equal to some constant K times square root of mu by 1 minus mu. Okay? Well, using 1 plus Q in this form to our equations, we obtain for LP, it's only checking if our rearranging is well. We obtain this. Yes, it's well because right hand side is constant. It was our assumption. It's well. And how it is diameter? For diameter we had this general equation. This equation we can, but 1 plus QP is this here. After rearranging, this is square root of mu by 1 minus mu, and here we have 1 minus mu by mu. Altogether, rearranging, and we obtain this here. This is the equation which is valid by our second version. It means if the lengths of pores are independent to packing density. Okay, we derived two different equations, especially for pore diameter. This is the important quantity, based on two quite different assumptions. Nevertheless, both equations are a little similar. See, in first variant, we obtain from dP, pore diameter, this equation. 1 minus mu by mu, I can write power to 1, it's possible, right? In the second, this here, it's this power to 0.5. It's similar, it's same structure, mathematical structure. Differences are only in the value of exponent, or 1 or 0.5. Nobody knows what's well. Maybe the variant 1 is not well in our situation, with our fibrous assembly. And the version 2 also is not well. But because the similarity may be that we can empirically generalize this knowledge and say the hypothesis that diameter, equivalent pore diameter dP, is possible obtained according to this equation where beside the parameter k, also parameter a is used. A is sometimes 1, sometimes 0.5, and maybe sometimes another value. This couple k and a are two parameters. I will discuss these parameters, how to obtain for variant 1, 2, and 3 this later. We can derive how is another quantities, because dp now, general dp is this here, and now we use for dp this expression. We must write that this is equal to this. This is a general equation. This is now our postulate equation. And from this equivalency, we obtain 1 plus qp is this here. Pore shape factor, so that the pore shape factor is this here. Length of fiber, total length of pores, general formula was this. Using qp from this expression, we obtain for LP this expression, and after rearranging this here, it's only mathematically rearranging, nothing more. Very easy. It is rearranging which you used on your high school before university. Well, so we have a formula for length, total length of pores 2. Because to illustrate it graphically, I have here 3 graphs. The first, all are on the abscissa of all is packing density, so that it is from 0 to 1, packing density mu. In the first graph, on this ordinate scale, is dp by d times 1 plus q by k. 1 plus q is constant, is parameter. Q is fiber shape factor. K is a suitable constant for this or that situation. With our material is constant too. D is equivalent fiber diameter, parameter value 2. So all this quantity is proportional to dp, is proportional to pore diameter, isn't it? Yes. You can see how it is. In variant 1, A is equal 1, you obtain the blue curve. The version 2, the variant 2, where A is 0.5, bring the red curve, also decreasing curve, but a little other shape. And general variant 3, I use, for example, A equals 0.75. Where it is here? Is the green curve, yeah? 0.75, something in between. Then you obtain this green curve. Acceptable, decreasing curves. How it is with length? No, shape factor. Here is a quantity 1 plus qp by k. So it is a linear function of qp. Yeah? Shape factor of fiber pore. In the version 1, this blue, we said the shape of pore is constant. So the pore shape factor must be constant. Therefore, the blue curve is independent to packing density. Version 2 said a length of pores is constant. In this version, the shape factor is increasing with packing density. The shape of pores in higher compressed material is more far from idea of ring, isn't it? More sawtoothed or something, so you can imagine it well. And in the version 3, using 0.75 on the place of A, it is also increasing function a little other shape. Now how it is with the total length of pores? It is shown here. Also, you can see that this quantity, which is possible to evaluate using our equations immediately, is proportional to total length of pore LP. All other is related to fibers. Well, you can see the version 1, the length of pores is increasing with packing density. In version 2, the length of pore is constant. This is our cigarette filter idea. So that the red curve must be constant, and by version 3, the green is a little other shape, but also increasing function. To this moment, we are living in the idea that we have a red pencil and we create some borders, fictive borders. We create the pores, isn't it, in our structure? But I'm sorry, I must your red pencil take back, because we have not. We haven't red pencil. We are not able to create pores. Who will to do it when we are not? It will create physical process which we studied. For each physical process for which is relevant the influence of pore dimensions, each physical process, this process have its own definition of pores, its own red pen and red fictive borders. Yeah? For example, by wicking, it's capillarity. This physical process on the same structure, same textile structure, define the pores other, so that the good dimension of pore is other than for example, filtration. Filtration process is other process. This process used an other pores, other pore diameters than the wicking process, for example. Yeah, on the same fibrous structure. Fibrous assembly have not only one type of pores. It is not well. It have only one character of space among fibers, no more. Yeah, the adequate pore diameter is sometimes higher, sometimes smaller, based on the process which used these pores. Can you imagine this situation? Yeah. Therefore, how to calculate our parameters k in version 3, k and a? We must calculate the suitable parameters in relation to the process which we solved. Yeah? When we solve, I don't know, capillarity effect, then we must do our equations which we use for capillarity, give our general equation for pore, maybe according to version 3. It's from the 3 versions is the best. And then we, on the whole mathematical model, we have 2 parameters which characterize good pore dimension, and this must be derived based on the study of this capillarity effect in laboratory. Yeah, using, for example, I don't know, statistical regression and so on. But it's every time so. Even our colleagues in mechanical engineering apply their equations for deformation of some metal objects. They derived a lot of such equations. But what is Young modulus? They must find in laboratory, isn't it? It related to situation and to material. The same is by us. Sorry, we have not our pencil, our red pencil. Red pencil have this or that, his own red pencil have this or that physical process. Okay? Some notes to possible applications I want to say in a next lecture, so that in the moment I thank you for your attention.